Hello everyone, my name is Hsieh. In this video, I will take a brief introduction of our paper, Contextual Proposal Network for Action Localization. The Temporal Action Localization task aims to provide a set of high-quality video segments as action proposals that potentially contain action events, and further identify the action class of each proposal. In this paper, we focus on generating high-quality proposals. Recent works use the temporal boundary prediction mechanism to generate the potential proposals by estimating their boundary probabilities. Our method similarly predicts boundary probability over the video sequence to discriminate potential action proposals. The boundary-based methods can provide flexible temporal boundaries. However, this approach generates noticeable false positive boundary predictions. To solve this issue, we first view a video as the combination of the foreground stats and the background stats. We observe that the boundary always occurs at the junction of the foreground and the background stats. That is, an action starting point occurs after the background stat and before the foreground stat. Similarly, an action ending point occurs after the foreground stat and before the background stat. Therefore, drastic changes of forwarding background stat and backward foreground stat support a high starting probability. And drastic changes of forwarding foreground stat and backward background stat support a high ending probability. We use two recurrent neural networks to collect bi-directional foreground and background stats. The collected foreground and background stats are further used to estimate boundary probabilities. In our experiments, this step enables our model to estimate the proposal boundaries of much less false positive. We also propose a feature-enhancing mechanism to generate a robust video segment representation concerning the long-range attention. Our feature-enhancing mechanism employs the inception-like module to concern the multi-scale temporal context for correlating the neighboring temporal information. Before capturing the multi-scale temporal context, our feature-enhancing mechanism also employs long-range attention to adjust the video representation. This table summarizes the comparison of our approach against state-of-the-art temporal action proposal methods. On the ActivityNet testing split, we improved AUC by 1.54%, and on the Filmer's testing split, our improvements range from 0.61% to 1.49% among AR at 200, AR at 500, and AR at 1000. This table shows the advantage of our context collection in the boundary scoring mechanism. Rule 3 demonstrates the extra background branch helps accurate boundary prediction with a performance gain of 1.2%. This figure visualizes the effects of employing our boundary scoring module. The top row images correspond to the center frames derived from local peaks of the boundary predictions, and the bottom four charts show the estimated boundary probabilities of the Bayesian and our model. The results show that our model contributes to estimating the more accurate proposal boundaries and less false positive estimations. And this figure shows an example of retrieving the high-quality proposals of our model on the ActivityNet dataset. In conclusion, our feature-enhancing mechanism captures the contextual information for generating a robust representation, and our boundary scoring mechanism associates the various scoring probabilities. Thank you for listening.